Good afternoon, everyone. Welcome to RSA. Our first speaker is going to be Junjae Chen. The session is Symmetric Cryptanalysis 1, and there's not going to be any physical speaker today, but they have a presentation.
Jie, a student from Beijing Institute of Technology. The title of my presentation is Improved Graph-Based Model for Recovery Superpoly on Trivial. A symmetric cipher can be viewed as a function fxv of an n-bit key x and an n-bit public variable v. For the v, we take a subset I of 1 to n and let Ti be the product of the elements Vi. Then we can decompose fxv as follows. Well, Pxv is called the superpoly. Let Vi1 to Vii take all 2 to the I possible values to construct a cube Ci. Then we have an interesting result that the sum of fxv over the cube Ci is equal to Pxv. For an attacker, the sum of fxv over the cube Ci can be obtained by requiring the encryption oracle, and once the attacker recovers Pxv, he can recover 1 bit of the key information. Now I will explain the cube attack based on graph model through a simple stream cipher. Here, Z is equal to Y1 multiplied by Y2. Y1 is equal to X2 plus X3. Y2 is equal to X1 plus X2 multiplied by X3. We can transform this simple cipher into a directed graph, where the nodes represent the variables in the cipher and the edges represent the operations between the variables. Here we use the black edges here to represent the linear operation, and the red the red edge to represent nonlinear operations. For each node in the graph, if we active only one black edge on or both two red edges, we obtain a trail that represents a monomial in the ENF of fxv. In this example, we can find a total of 4 different trails, and we can use these trails to recover the ENF of fxv, that is z equals to x2 multiplied by x3 plus x2 multiplied by x3 plus x1 multiplied by x2 plus x1 multiplied by x3 equals to x1 multiplied x2 plus x1 multiplied x3. Next, I will explain how to convert the graph into a MLP model to achieve automatic solving. The first constraint states that at most one outgoing edge can be activated for any node. The second constraint limits a trio must start from the root and end with a leaf node. The third constraint states that the two child node corresponding to a nonlinear operation must both appear in a chair. With these three constraints, we can recover the ENF of the stream cipher based on all feasible solutions of the model. However, in the cube attack, the attacker only needs to recover the superpoly. Therefore, we need to add two additional constraints. Each leaf node in I must be activated, and the leaf node outside of I and K cannot be activated. Next, we will introduce two techniques for simplifying the MLP model. The first one is pruning patterns. Subtrails with the same start node and end node must lead to an even number of trails representing the same monomial. Here is the example in the toy cipher. These two trails both lead to x2 multiplied by x3, and they will eliminate themselves in the ENF. We can add the following constraints to prove these trails. Now we need to apply this technique to trivial. The pseudocode of the initialization of trivial is as follows. And this is the DAG of around trivial. We have obtained the following pruning pattern by observation. Both of these subtrails start from x1, x3, and x4, and end at y1, y2, and y3. It is obvious that these two subtrails will lead to an even number of identical monomials. We can find this pattern since the SIs are not far apart, so we have the question: are there more patterns in trivial? To solve the problem, we proposed a localized graph model and made some changes to the constraints. The objects of the model is to find the subtrails with the same starting and ending nodes. The sum of xij must equal 1 instead of less than or equal to 1. And the loose node is also replaced by a set of nodes. Finally, we get 12 patterns with 3 node roots and 2 layers. Now I will introduce another simplification technique. In 840 rounds of trivial, we can obtain 12,909 feasible solutions through the graph model. If we add the 3 consecutive bit pattern in the model, we can obtain 5,953 feasible solutions, which means that 6,956 trails are pruned. However, the sum of the activations of this node decreased by more than 4,000, and for these 3 nodes, more than 5,000, and for this, more than 4,002. That means subtrails in 3CBP might appear multi times in a trail. Here is an example. The constraints in pink area and green area are redundant. We only need to add the constraint in pink area or in green area. Now we give the definition that T be the number of solutions of a graph-based model without any pruning. That T prime and C be the number of solutions and the pruning constraints of a graph-based model with pruning. The pruning trail constraint ratio is defined as the ratio of T minus T prime to C. The PTCR indicates the average number of trails eliminated by pruning constraints. To reduce the redundant constraints, we only keep the pruning constraint at the terminal node and discarding others. For the example mentioned before, we keep the constraint in the green area and discarding those in the pink area. And here is our result. The M is the graph-based model without any pruning patterns. The M prime is a model with pruning patterns everywhere, and the M double prime is the model with pruning patterns only at the terminal node. We can see that the PTCR has been improved by 7 to 10 times. But we encountered another problem soon. Our server only has 94 GBIM and we cannot solve the 842 round model. To solve this problem, we propose the nested graph-based model. Let R be a set of loops with multi-nodes. We calculate the ANF of Z with respect to SR minus 2 and add all monomials in the ANF to R. For each element in R, we construct a graph-based model with time limit tau. If the model can be solved, the information of superpoly is obtained. And if the model cannot be solved in time limit, then add the elements one round decomposition to R. The full superpoly can be recovered when the R is empty. With this method, we improve the round to 843 with the limited memory. Finally, let me summarize our work. We proposed a local graph-based model to find more pruning patterns. As a result, we get 12 patterns with 3 node root and 2 layers. We reduced the redundant pruning constraint significantly. The pruning efficiency of the constraints are improved by 7 to 10 times. And we combine the nested framework and the graph-based model. The solver round on the limited memory is improved by 2 rounds. My presentation is over. Thank you for your attention.
Grados, I'm going to present the work Fully Automated Differential Linear Attacks Against ARX Ciphers. ARX ciphers are those that have as components modular addition, rotation, and XOR operations. And differential linear attacks are those attacks that combine differential and linear attacks. In this work, we propose an automated tool to help to mount differential linear attacks. So, what is differential linear cryptanalysis? In differential linear cryptanalysis, we are looking for a certain property in a specific cipher called differential. And the differential basically is a pair where the first elements correspond to the input and is called input difference, and the second one corresponds to the output and is called output difference. This happens with a certain probability, for example, 2 to the minus 1 in this case. To check if a cipher has this property, we need to generate a random state XOR with the input difference, and after that, we need to apply the cipher and check if the XOR of the results is equal to the output difference. If this happens, then this cipher has this differential property. It is possible to find this property, the differential property in a mathematical way. The answer is yes. To do that, we need to see how the difference propagates through the components of the cipher, and after that, see how this propagation occurs through the rounds and in consequence to the entire cipher. Here the color red means difference, and in the case of the rotation this happens with probability 1, but in the case of the modular additions this happens not always with probability 1. Of course, there are some theorems by Littman and Chiho stating the probability of the propagation of the difference through the modular addition. So in that case, in the case of the XOR operation, the propagation also occurs with probability 1 because it is a linear operation. Okay, so can we automate the search for differential properties? The answer is yes. There are several techniques to do so. For example, MIL, SAT, NCP, and among others. Kai-Fu et al. In 2016 used MIL techniques. They propose a way to translate the theorem 1 and theorem 2 from Littman and Chiho to a set of inequalities, of linear inequalities. Why to a set of linear inequalities? Because in MIL we need to translate problem to a set of linear inequalities, and after that we can solve these problems. Of course, we want good differentials to mount attacks. So what are good differentials? Are those that have a high probability. So this is why here we are representing the exponent of the differential by p, and it is involved in the set of linear inequalities, as you can see in this function f. So in the case of specs, there is one modular addition per round. This is why here I am representing the exponent of the probability of every modular addition by P1, P2, P3, and P until PR, in order to find the probability of the entire cipher under certain assumption. Then we need only to assume the exponent of these exponents. Okay? In the case of linear cryptanalysis, we need to search first for a property called linear approximation. The first element of the pair now corresponds to the input and is called input mask, and the second one is called output mask. So to check if a certain cipher has this property, what we need to do, again, we need to generate a random state, we need to apply the cipher, and we need to apply the mask. Okay? And to check the correlation, what we need to do, we need only to XOR the bits in the input and the output max and check if this XOR operation is equal or not to 0. We need to repeat this in order to check if this happens with a correlation near to the correlation of the linear approximation, that is 2 to the minus 1. So how to find linear approximations automatically in using MIL? You can see the paper from Kai-Fu et al. In 2016 to see more details about the techniques to find this or to automate this search for linear approximation. Okay, so now regarding the differential linear cryptanalysis. So what is differential linear cryptanalysis? Here we need to search for a certain property of the cipher called differential linear distinguisher or differential linear property. Again, this distinguisher, this property has a certain correlation, okay? For example, here, 2 to the minus 1. Also, the first element of this pair is called input difference, while the second one is called output mask. And to check if a certain cipher has this property, what we need to do? We need to generate a random state XOR with the input difference, and after that we need to apply the function f, okay? And after that we need to XOR the results, and once we XOR the result, we need to apply the output mask, okay? And then after we apply the output mask, we need to check now if the correlation is 2 to the minus 1. To check if the correlation is 2 to the minus 1, then we need to check if the XOR of the bits that are active in the output mask is equal to 0. So we need to repeat the process several times to see if this correlation happens with probability 2 to the minus 1. So how to find differential linear distinguisher? To find differential linear distinguisher, we can combine the differential and linear techniques. We can start, for example, with the differential in the differential pair. For example, here, this is the differential pair for the first n rounds, and this is called the top pair. And after that, we can search for the linear approximation, for example, for m rounds. This is called the bottom pair, and we need to connect these two pairs, of course, by using a differential linear distinguisher, and we can do so experimentally. The total correlation of the distinguisher will be then PRQ squared, while the complexity to distinguish from a pseudo-random permutation is this formula here, okay? So, in Wang et al. In 2022 proposed a differential linear distinguishers against expected 264. They start in the middle by looking all the possible differential linear distinguishers with one active bit in the input difference and one active bit in the output mask. By doing so, they found these two positions that I'm showing in red here, and after that they extend backward 2 rounds to find the differential pair and forward 1 round to find the linear approximation. Using the aforementioned formulas, it is possible to compute the total correlation and also the complexity of to distinguish a cipher from a pseudo-random permutation. But what is the problem here? The problem here is that they are limiting the number of active bits on the input difference and also in the output max of the middle part to 1, okay? However, not always happens that the better correlation can be obtained using these limitations. There are more papers from 2022 limiting this number of active bits in the input difference or output max, as you can find then in the appendix of our paper. Okay, so we propose then a way to automate the search for differential linear distinguishers, relaxing this limitation. This is one of our contributions, and to the best of our knowledge, this is the first paper approaching the automatization to search differential linear distinguishers. Our techniques use mixed integer quadratic constraint programming, okay, as we can see later. Okay, recalling the differential linear cryptanalysis, we need to compute the correlation that in this case is 2 to the minus 3 by XORing the active bits in the output bus and checking if it is equal to 0 or not. Can we estimate this correlation using two differential linear distinguishers? So the answer is yes. We can do so by splitting the differential linear distinguisher into two. In this case, we need to create a new output mask for every distinguisher with only one active bit in the output mask. For example, if the first distinguisher happens with correlation 2 to the minus 1, or 2 to the minus 2, sorry, and the second one with 2 to the minus 1, then we can combine again these two distinguishers in order to obtain the initial correlation by applying the peeling-up lemma, assuming independence between the two terms involved in the output mask. Okay, now that we know how to compute the correlation in the middle part of the differential linear distinguishers, we are going to see how to connect the top part with the middle part. To connect them, we need to translate the binary number representing the output difference of the third part into correlation, which is the probability of the output difference B1 knowing that it is 0? Of course it is 0. Using the formula of the correlation that involves the probability that is in the slide, we can compute then the correlation for all the binary values 0 and also for the value 1. And in the case of the value 1, we have the correlation will be, of course, 1. Okay? Okay. We need to propagate now the real numbers, okay, through the components of the ciphers. In the case of the modular addition, the propagation of this correlation are expressed in several formulas. One formula per each bit representing the output of the modular addition. Of course, in this formula is involved the carry. And also in this formula, you can see that there are some quadratic terms, okay? And this is why we use the mixed integer quadratic constraint programming, okay? So to propagate the difference that are now real numbers through the components of the cipher, we have some formulas to compute this propagation in the paper for the linear operator, for the rotation operator, for the modular addition that I just explained before, and also for the XOR operation that is also a linear operator. As you can see now, I am representing with a gradient from white to red the propagation of the correlation. Why? Because now we are talking about correlations that are real numbers. So in this picture really actually is representing one round of the spec cipher. So once we know this, it is easy then see how occurs the propagation of these real numbers through several rounds. Okay, and to connect the middle part with the linear part, we need to use the input mask and of the linear part. Specifically, we need to apply this input mask in the output of the differential linear part. And here I am representing with a color with color green, the active bits in this input mask of the linear part. So, and as I mentioned before, to compute the correlation of the middle part, we need to multiply the active bits in the input mask, okay, of the linear part. And we need to multiply them, assuming, of course, that there is an independence of the bits involved in the input mask to apply the peeling-up lemma. So putting all the probabilities and correlations together, you can see that we have that in the differential part, we have the pattern 2 to the minus something, and in the linear part also 2 to the minus something, but in the middle part, it is not happening. So to facilitate our computations, we need to do some mathematical operations in order to express these correlations in terms of power of 2. And after those some math, okay, the exponent of the correlation of the middle part is minus log in base 2 of the value absolute of R, where R is the value of the correlation. So we need to minimize this function because if we want a good differential linear distinguishes, we need a small exponent. Okay, so then we put in the paper some ways to approximate this Logi function by using some PSY linear approximations. Okay, and why? Because normally in MidSolver there is not this approximation as a built-in function, as a built-in method. And this is why we need to approximate this Logi function by using PSY linear approximations. Okay, now putting everything together, we can see the probabilities of and the correlations as power of 2. So in order to have a good differential linear distinguishers, we need to minimize the sum of the exponent of the probabilities and correlation of the three parts. Okay, so we apply our techniques to expect TT264, and here are some results. For 9 rounds, we obtain a better practical correlation in comparison of the past differential linear distinguishers. Specifically, we obtain the correlation of 2 to the minus 7.3, while in the state of the art, this value is 2 to the minus 8.93. For 10 rounds, we also improve the state of the art from 2 to the minus 13.9 2 to the minus 12. And for 11 rounds of this SPEC3264, we obtain a distinguisher with correlation of 2 to the minus 16 and complexity 2 to the and complexity 2 to the 29 to distinguish a cipher from a pseudo-random permutation. Using the previous distinguishers, we mount also key recovery attacks against 13 and 14 rounds, and again we improve the state of the art from a time complexity 2 to the 60.99 to 2 to the 58 in the case of 14 rounds. Okay, and regarding the data complexity, we improve the data complexity for these 14 rounds from 2 to the 31.75 to 2 to the 31. So finally, we have here the conclusions. In this work, we consider differential linear attacks against AURAC ciphers and how to model these ciphers in the real domain. We propose a new automatic tool to search for differential linear distinguishers, and this tool uses MILP and mixed integral quadratic constraint programming techniques. And to the best of our knowledge, this is the first attempt to fully automate the search for differential linear distinguishers. By using this tool, we improve previous differential linear distinguishers and previous differential linear attacks against SPEC3264. We believe that our techniques can be applied to SPN cipher. So thank you for hearing me.
That concludes our session today. Thank you for coming out today.